So this video is going to have a look at the blue proof up above, and that's the proof using vectors we're going to use, that the diagonals of a parallelogram meet at right angles if and only if it's a rhombus. So the if and only if statement is not something we generally use in extension 1 in high school. It's not something you might use at extension 2 or at university, but we're going to look at the proof going both ways. So we want the proof to go that way and we want the proof to go that way. So if and only if means we're going to show that the diagonals of a parallelogram, if they're made at right angles, then it's a rhombus, but we're also going to show that the diagonals of a parallelogram, if they are a rhombus, then they meet at right angles. So we want the proof to work both ways. So we're going to see if we can get that to work. Now, the diagonals of a parallelogram. So we've got O, A, B, C is a parallelogram. Okay, so we're given that. And we've got diagonals of that parallelogram, and they're going to be AC and OB. I generally try to go alphabetical. So let's let our vectors go in the direction OA, AB, OC, CB. That one's not alphabetical, is it? But we'll let it go that way. And I'm going to go the direction OB, and we'll go AC. Just so that it matches up with our already pre-prepared vector additions on there. Okay, so let's think about what we know. Now, if we're looking at vector addition, we need to look and double check that our V minus U and our U plus V are correct. So if we look at the bottom triangle over here, our OAC, using the parallelogram method, if we've got V and we've got minus U, we get vector AC. So V minus U, yep, that's right. So that one's correct. So the vector AC is called V minus U. If we have a look at our other one here, again, you can use the triangulation method. We might use that for this one. We've got vector V plus vector U is U plus V. Okay, so that's good. So those two are correct. So we've named those. Now, going back to what we're looking at, the diagonals of a parallelogram meet at right angles if it's a rhombus, and it's a rhombus if it's a right angle. So we need to figure out what we can do about that. So when we're looking at things meeting at right angles, then we're looking at the dot product. So we want to have a look at the dot product of the diagonals. So what are our diagonals? Our diagonals are OB and AC. So we want to have a look at the dot product of those. Thinking back to our rules for dot product, that looks at cos of theta, and generally, always, if things are perpendicular or they meet at 90 degrees or right angles, then our dot product is going to equal 0. And that's what we want to show in this case. So the dot product of OB and AC is going to be, well, we know that OB is the vector V plus U. And we're going to show that as a dot product of V minus U. Okay, so there are our two diagonals. So we need to expand that out. So expanding that out, we're going to have V dot V plus V dot U minus U dot V minus U dot U. So because it's commutative, V dot U and U dot V are going to be the same. So they cancel each other out. And so what we end up with is vector V dot vector V minus vector U dot vector U. Okay. Now if we think back to what that actually means, when we're multiplying two vectors together, what we're going to end up with is the magnitude of one times the magnitude of the other minus the magnitude of one times the magnitude of the other, or you might remember it straight off that it's the magnitude of that vector squared, magnitude of the other vector squared. So you can go straight from here down to here if you remember that. Okay, so remembering that we're looking at the dot product of those diagonals. So we've got that being our final solution here. So we need to go both ways in our proof. So if vector OB is perpendicular to vector CA, then the dot product is 0. Okay, so if they're perpendicular, the dot product is 0. if that is the case, if the dot product is 0, and then what we're going to be saying is that the magnitude of v squared is going to be equal to the magnitude of u squared, or the magnitude of vector v is going to be equal to the magnitude of vector u. And therefore, so opposite sides are going to be equal. Okay, so therefore we're going to have a rhombus. Okay, so OABC then will be a rhombus. But going the other way, if OBC is a rhombus, and we know that the properties of a rhombus, the opposite sides are going to be equal in length and parallel, and then we would say that the magnitude of u would be equal to the magnitude of v. Therefore, we would say that OB is going to have a dot product with CA of 0. So we could say, therefore, that they are perpendicular. So the proof works both ways.